Learning objectives. At the end of this topic, you will be able to understand irrational numbers, understand real numbers and their decimal expansions. Introduction. Welcome to the chapter Number System. You already know how to represent various types of numbers on a number line. Pick up only natural numbers like 1, 2, 3 and so on and drop them into the box. Now this box contains infinitely many natural numbers. We denote this collection of natural numbers by the symbol capital N. Now pick up 0 and put it into the box. Now it's a collection of whole numbers, which is denoted by the symbol capital W. Put all the negative integers into this box. Now this box contains a collection of all integers and it's denoted by the symbol capital Z. Observe. Still, a few numbers are left on the number line. There are numbers like 1 by 4, 1 by 2, 3 by 4, and so on. Put all such numbers also into this box. It will now be a collection of rational numbers. The collection of rational numbers is denoted by capital Q. Rational comes from the word ratio, and Q comes from the word quotient. For example, minus 15 can also be written as minus 15 by 1. Here P is equal to minus 15, Q is equal to 1. Therefore, the rational numbers also include natural numbers, whole numbers, and integers. Consider another example. 1 by 2 is equal to 2 by 4 is equal to 3 by 6 is equal to 5 by 10, and so on. These are equivalent rational numbers or fractions. If P and Q have no common factors other than 1, then we call P and Q as co-prime. We know there are infinitely many rational numbers between any two given rational numbers. But there may be some numbers in the number line that are not rational. The numbers which are not rational numbers are called irrational numbers. In this chapter, we are going to discuss about these numbers. Irrational numbers. Irrational numbers cannot be written in the form P by Q, where P and Q are integers and Q is not equal to 0. We know there are infinitely many rational numbers on the number line. Similarly, there are infinitely many irrational numbers too. These numbers are some examples of irrational numbers. Again, we consider the box which contains rational numbers. Now put all irrational numbers into this box. Will there be any number left on the number line? No. Now this box contains collection of all rational and irrational numbers together. What will you call a collection of all rational and irrational numbers together? We call it as the collection of real numbers, which is denoted by capital R. Therefore, a real number is either rational or irrational. So we can say every real number is represented by a unique point on the number line. Also, every point on the number line represents a unique real number. This is why we call the number line the real number line. Representing irrational numbers on the number line. Here we see how to represent a root 2 on the number line. In this number line, here 0, 1, 2, and here minus 1 and minus 2. Now draw a unit square. It's a simple square. All the sides have 1 unit. We know in a square all the sides have equal length and the angles are all 90 degrees. If we measure each side, the length of the side is 1 unit. Observe in triangle BDC. It's a right-angled. BD is the hypotenuse. It's a side opposite to the 90 degrees. Since it is a right-angled triangle, we apply Pythagoras Theorem here. We can write it as BD square is equal to BC square plus CD square. We know BC is 1, so we write it as 1 square. Plus CD is also 1, so we write 1 square. It becomes 1 plus 1, which is equal to 2. So here BD square is equal to 2. Therefore, we write BD is equal to square root 2. This length, that is the length of DB, is equal to square root 2. Now bring the square on top of the number line, the point D, which actually coincides with the point 0. Now we lift the square and put on the number line as shown here. We already know the length of dB is square root 2. Now take the compass and place one sharp end point at D, which is now the origin 0 here, because it is a unit square. So D coincides with 0 and C coincides with mark 1. Now extend the compass to B and then draw an arc like this by cutting the number line at a point. We denote this point as X. In this case, the length of BD is equal to OX or DX. Why? Because this will be the same radius. This will be an arc, so it has the same radius. So we can write BD is equal to DX, which is equal to OX. Therefore, OX is also equal to root 2. So this point represents the square root 2 on the number line. Representing root 3 on the number line. How do we represent irrational number on the number line? Draw a unit square on the number line. In an example of root 2, we have seen the length of OB is root 2 by Pythagoras Theorem. Now we have to show square root 3 on the number line. Draw a line from B that is perpendicular to the line DB. Now join the line, the perpendicular line, and D as shown here. Let's call it as Y. In triangle DBY, again applying Pythagoras Theorem, we can write dy square is equal to by square plus bd square. Here by is 1 square unit and bd is root 2 square unit. So write 1 square plus root 2 the whole square. 1 square is nothing but 1 plus root the whole square. This 2 and square root will get cancelled, so we get a 2 here. So we get dy square is 3, or in other words, dy is square root 3. Therefore, the length dy is square root 3. Again, taking the example of compass, this is a pointed end and we put a pencil here. Place the pointed end on the origin, extend the compass to Y. Place the pointed end at Y. From Y, draw an arc. This arc will cut the number line at some point and we call it as X. The length of dx is equal to OX. This is nothing but equal to dy because we have drawn an arc. So dy and dx or OX have the same radius and this is an arc. So that we can write OX is equal to square root 3. So we represent root 3 here. This is how we get square root 3 on the number line. In the same way, you can locate n for any positive integer n after n minus 1 has been located. Real numbers and their decimal expansions. Decimals in real life. We cannot forget the decimal numbers. We always use decimals like prices of various things in decimals. For example, milk pouches for rupees 18.50, weight, volume, and even height are written in decimals. Height of this person is 1.6 meters and his weight is 52.5 kilograms. The volume of this milk packet is 500 ml or 0.5 liters. Are the decimals rational numbers? We know the rational numbers are represented by P by Q, where P and Q are integers, Q is not equal to 0. So, P by Q is a rational number, and we can easily convert fraction to decimals by division method. For example, let's divide 4 by 5. We cannot divide 4 by 5, so we put a 0 after 4, and we put a decimal point in the quotient. Now 8 times 5 is 40, with the quotient 0.8. Any fractions with a denominator as multiple of 10th can be converted into decimal directly. For example, 1 by 10 is equal to 0.1 and 1 by 100 is equal to 0.01. As the point gets shifted by 2 places to the left if we divide it by 100. Does it mean all the decimals are rational numbers? To find, we need to know the decimal numbers first. When we divide 4 by 5, we get 0.8. In this case, we get a remainder as 0 and division ends. Thus, 0.8 is a terminating decimal number, as the decimals terminate or ends after a certain value. But not all decimal numbers terminate this way. For example, 1 divided by 3. Now let's divide 1 by 3. Since 1 is smaller than 3, we put a 0 after 1 and point in the quotient. Now 3 times 3 is 9. 10 minus 9 is 1, so the remainder is 1. Again, we bring in 0, and 3 times 3 is 9. 10 minus 9 is 1. Again, the remainder is 1. So this division would go on like this. 0.333 and so on would be the quotient. Such decimals are called non-terminating decimals. In this particular decimal, 3 is repeating itself. So we can write it as 0.3 with a bar over the number 3. This means this decimal would never terminate and 3 would keep on repeating itself, and thus we get the 0.333 and so on. You know, not just one digit. More than one digit may repeat too. For example, when we divide 1 by 7, then we get a quotient as 0.142857142857 and so on. What do we observe here? Part of the decimal number is repeating itself continuously. So we keep this whole repeating decimal part under a bar. Thus we get the answer as 14287. Of all the digits after decimals are under the bar. We say that this expansion is a non-terminating, recurring. Does that mean all the decimals are rational numbers? No. Few non-terminating decimal numbers don't have any repeating part, like 1.41421352 and so on. This non-terminating decimal cannot be represented as a ratio of two integers. That is why we cannot represent in the form of P by Q, where PA and Q are integers. Look, this is a non-terminating decimal, but it doesn't have any repeating part. Such decimals are called non-terminating, non-recurring decimals. You know this is not a rational number, so we call it as irrational number, and also this is the value of square root 2. Square root 2 and square root of 3, etc. are irrational numbers. Let us revise. So far we have learnt there are two kinds of decimals. Terminating decimals, which end after certain value like 0.8, and non-terminating decimals that do not have any end. In certain non-terminating decimals, the digits can repeat themselves, and these are recurring non-terminating decimals like 1 by 3, which is equal to 0.3 bar, which means 3 repeats continuously, and non-recurring non-terminating decimals. The decimal digits do not repeat continuously. So, the non-terminating, non-recurring decimals, which cannot be represented as a ratio of two integers, that is in the form of P by Q, are called irrational numbers, like the square root of 2 is equal to 1.4142 and so on. In short, not all decimal numbers are rational numbers, but all rational numbers can be converted into a decimal number. Let's see a few examples here. Show that 2.54632 is a rational number. In other words, express 2.54632 in the form of P by Q, where P and Q are integers and Q is not equal to 0. We have 2.54632. We already know how to convert decimal numbers to rational numbers. So this we can write it as 25462 divided by 1000000. Hence, it's a rational number. Now let's consider the next example. When the decimal expansion is non-terminating, recurring. Show that 1.333 etc. is equal to 1.3 bar. Can be expressed in the form P by Q, where P and Q are integers and Q is not equal to 0. Since we do not know what 1.3 bar is, let's call it as X. X is equal to 1.3333, etc. Here only one digit is repeating, so we multiply X by 10. 10X is equal to 10 into 1.3333, etc., which is equal to 13.333, etc. We can also write 13.333, etc. as 12 plus x, since x is equal to 1.3333, etc. Therefore, 10x is equal to 12 plus x. Solving for x, we get 9x is equal to 12. This implies x is equal to 12 by 9. Hence, x is equal to 4 by 3. Now let's consider another example. Show that 1.232323, etc. is equal to 1.23 bar can be expressed in the form p by q, where p and q are integers and q is not equal to 0. Let x be equal to 1.23 bar. Since two digits are repeating, we multiply x by 100 to get 100x is equal to 123.2323, etc. This we can also write it as 100x is equal to 122 plus 1.232323, etc. So 100x is equal to 122 plus x. Since x is equal to 1.232323, etc. Solve for x. We get 100x minus x is equal to 122. Therefore, 99x is equal to 122 by 10. We get x is equal to 122 by 99. So, every number with a non-terminating recurring decimal expansion can be expressed in the form p by q, where p and q are integers. Now let's consider another example. Find three different irrational numbers between the rational numbers 3 by 7 and 6 by 11. Solution. We have 3 by 7 is equal to 0.428571 bar and 6 by 11 is equal to 0.54 bar. We observe that in the first decimal place, a has digit 4, b has digit 5, therefore a is less than b. In the second decimal place, a has digit 2. So, if we consider irrational numbers, x is equal to 0.430, 4300, 43000, etc. Y is equal to 0.440, 4400, 44000, etc. And z is equal to 0.450, 4500, 45000, etc. So we find that a is less x, less than y, less than z, less than b. Hence, x, y, and z are required irrational numbers. Representing real numbers on the number line. You've already seen that any real number has a decimal expansion. This helps us to represent it on a number line. Let's see how to represent it on the number line. Suppose we want to locate 3.445 on the number line. We know that 3.445 lies between 3 and 4. So let's look closely at the portion of the number line between 3 and 4. Suppose we divide this into 10 equal parts and mark each point of division as shown here. Then the first mark to the right of 3 will represent 3.1. Second point will represent 3.2, and so on. In this figure, you might be finding some difficulty in observing these points of division between 3 and 4. To have a clear view of the same, you may take a magnifying glass and look at the portion between 3 and 4. Now, 3.445 lies between 3.4 and 3.5. Now let's focus on the portion between 3.4 and 3.5 as shown here. Again, we divide this into 10 equal parts. The first mark will represent 3.41. The next point will represent 3.42, and so on. To see this clearly, we magnify it as shown here. Again, 3.445 lies between 3.44 and 3.45. So let's focus on this portion of the number line. We divide it again into 10 equal parts. We magnify it to see it better. The first mark represents 3.441. The next one represents 3.442, and so on. So 3.445 is the fifth mark in these subdivisions. We call this process a visualization of representation of numbers on the number line through a magnifying glass as the process of successive magnification. So, we have seen that it is possible by sufficient successive magnifications to visualize the representation of a real number with a terminating decimal expansion on the number line. Let's try another example and visualize the position or representation of a real number with a non-terminating recurring decimal expansion on the number line. Visualize the representation of 4.27 bar on the number line up to 5 decimal places, that is 0.277777. First, we see 4.27 bar is located between 4 and 5. In the next step, we locate 4.27 bar between 4.2 and 4.3. To get a more accurate visualization of the representation, we divide this portion of the number line into 10 equal parts and use a magnifying glass to visualize 4.27 bar lies between 4.27 and 4.28. To visualize 4.27 bar more accurately, we again divide the portion between 4.27 and 4.28 into 10 equal parts and use a magnifying glass to visualize that 4.27 bar lies between 4.277 and 4.278. Now to visualize 4.27 bar still more accurately, we divide the portion between 4.277 and 4.278 into 10 equal parts and visualize the representation of 4.27 bar as shown here. Notice that 4.27 bar is located closer to 4.2778 rather than to 4.2777. Operation on real numbers. Let A be greater than 0 be real number. Then A is equal to B means B square, which is equal to A and B is greater than 0. Now let's see how to find root x for any given positive real number x geometrically. For example, let's find square root of 2.5 geometrically. Take any point A, then draw a line AB is equal to 2.5 units. Now extend AB to point C such that BC is equal to 1 unit. Now find out the midpoint of AC, say point O. Using O as a center, draw a semicircle with radius OC. Draw a straight line from point B that's perpendicular to AC and intersecting the semicircle at point D. Hence the length of BD is square root of 2.5 units. More generally, how to find out the square root x geometrically where x is any real number. Take any point A, then draw a line AB equal to x units. Now extend AB to point C such that BC is equal to 1 unit. Now find the midpoint of AC. The total length of AC is x plus 1, so mark the midpoint of AC, say point O. Consider AC as the diameter, OA and OC are radius. So from center O, draw a semicircle on AC. Next, draw a straight line from point B that's perpendicular to AC and intersecting semicircle at point O. Now we find the length of BD. We can prove this result using the Pythagoras Theorem. In triangle OBD is a right-angled triangle. Also, the radius of the circle is x plus 1 by 2 units. Therefore, OC is equal to OD is equal to OA is equal to x plus 1 by 2 units. Now, OB is equal to x minus of x plus 1 by 2. Simplify this, we get x minus 1 by 2. So, by the Pythagoras Theorem, we have BD square is equal to OD square minus OB square is equal to x plus 1 by 2 the whole square minus of x minus 1 by 2 the whole square. Simplifying this, we get 4x by 4. Cancel the 4's. We get BD square is equal to x. This shows that BD is equal to root x. If you want to know the position of root x on the number line, draw a number line with b as 0. We know the length of BC is 1, so we mark C as 1, then 2, 3, 4, and so on till plus infinity. Similarly, mark -1, -2, -3, -4, and so on till minus infinity. We already know the length of BD is square root x. Now we have to find square root of x on the number line. Take the compass, put the pencil in it, place the sharp pointed end at B. Extend the other end of the compass till D. Draw an arc with B as center, BD as radius, which intersects the number line at some point. We consider this point as y. Since BD is square root x, the length of BY is also square root x, because we have drawn an arc from D with center at B. Hence y represents root x. From this we learned square root of any positive real number can get them on the number line. We now list some identities relating to square roots, which are useful in various ways. Let's look at examples of these identities. Consider the first law. Square root AB is equal to square root of A into square root of B. Let's verify this with the help of an example. Root 16 into 25 is equal to root 16 into root 25. Solution. We have to prove that LHS is equal to the RHS. LHS is equal to square root of 16 into 25 is equal to square root of 400, which is equal to 20. RHS is equal to square root of 16 into square root of 25 is equal to 4 into 5, which is equal to 20. Thus, both the sides are equal. The second law. The square root of A divided by B is equal to square root of A divided by square root of B. Example. Square root of 81 divided by 9 is equal to square root of 81 divided by square root of 9. Left-hand side is equal to square root of 81 by 9 is equal to square root of 9, which is equal to 3. Similarly, on simplifying the right-hand side, we get the answer as 3. Thus, both the sides are equal. The third law is the product of sum and difference of a square root of A and the square root of B is equal to A minus B. Let's verify this with an example. Now simplify the left-hand side by expanding it. These two terms get cancelled. Now apply the law 1. Let's simplify this expression. On simplification, we get 4 minus 2 is equal to 2. On simplifying the right-hand side, 4 minus 2 is equal to 2. Hence, this example is verified. The fourth law is A plus the square root of B into A minus square root of B is equal to A square minus B. Let's verify this law with an example. Left-hand side of this expression is 4 plus square root of 2 into 4 minus square root of 2. Now simplify the left-hand side by expanding it. These two terms get cancelled. Again, apply the first law. We get 16 minus 2 is equal to 14. On simplifying the right-hand side, we get the same answer. Thus, both the sides of this example are equal. Let's consider one more example using the fourth identity. Rationalize the denominator of 1 by 3 plus root 2. To rationalize this denominator, we use the fourth identity. Multiply and divide 1 by 3 plus root 2 by 3 minus root 2. On simplifying this, we get 3 minus root 2 by 5. Based on this example, you can rationalize the denominator by using the fourth identity. The fifth law is square root of A plus square root of B into square root of C plus square root of D. Now let's verify this law by using an example. First, we will simplify the left-hand side of the example. Then expand this expression. Let's simplify this by using the first law. This is equal to the right-hand side of this example. Thus, both the sides are equal. The sixth law is the square root of A plus square root of B, the whole square, is equal to a plus 2 times square root of ab plus b. First, we'll simplify the left-hand side of this example. Then expand this expression. Apply the first law and simplify this. Now this is equal to the right-hand side of the example. Thus verified the example. Laws of exponents for real numbers. Real number is nothing but a collection of both rational numbers and irrational numbers. We know rational numbers are represented as q. These numbers are in the form p by q, where q is not equal to 0. These are some examples of rational and irrational numbers. Can we apply laws exponents real numbers? Let's verify the first law. Consider the term 2 raised to the power of 4. Here 2 is called the base, 4 is called the exponent. This term can also be written as 2 multiplied 4 times. Now let's multiply the term with 2 raised to the power 2, which is equal to 2 multiplied 2 times. The product of the term is 2 raised to the power 6. Can you see the exponents of the relations to the three terms? Yes, the exponent 6 is equal to sum of 4 plus 2. Next, verify the second law of exponents. Here we divide two exponents of terms. The numerator and the denominator can also be expressed as follows. On simplifying, we get 5 to the power 4 minus 2 is equal to 5 to the power 2. Do you see the relationship between the exponents? Yes, 4 minus 2 is equal to 2. From this example, we can generalize the second law. Now verify the third law of exponent. Consider the example 5 raised to the power 2, the whole power 3. This can also be written as 5 to the power 2 into 3, which is equal to 5 to the power 6. Now let's verify the fourth law. Consider the example 2 to the power 3 into 5 to the power 3. This we can write it as 2 into 5, the whole to the power 3, which is equal to 10 to the power of 3. What is a to the power of 0? The number 1 to the power 0 is equal to 1. 2 to the power of 0 is equal to 1. 4, 0, 5, 0, power 0 is also equal to 1. In general, we say a to the power of 0 is equal to 1. That is, any positive real number raised to the power 0 is always equal to 1. So far, we have seen in each of these cases, the exponents are all in the forms of real numbers. What happens if we have number 1 by a to the power n? This we can write it as a to the power 0 by a to the power n, since a to the power 0 is equal to 1. This we can expand it as a to the power 0 minus n, which is equal to a to the power of minus n. This is similar to the second law. Now we can extend the laws to negative exponents m and n. For example, 2 raised to the power 3 multiplied 2 raised to the power minus 2. Using the first law, this can be written as 2 raised to the power 3 minus 2. After simplifying, we get 2. Next example, 11 to the power 5 divided by 11 to the power minus 3. Apply the second law. Simplify this, we get 11 to the power of 8. The third example is 5 to the power of minus 2, the whole power of 5. Here we apply the third law. We get 5 raised to the power minus 10. This can be written as 1 by 5 to the power 10. Consider the fourth example. 3 raised to the power minus 10 multiplied 4 raised to the power minus 10. Observe here the bases are different and the exponents are the same. So we use the fourth law. We write it as 3 multiplied 4, the whole power minus 10. This becomes 12 raised to the power minus 10. We know negative power can also be written as 1 by 12 to the power 10. How would you solve even when the base is a positive real number and exponents are rational numbers? We know that n square root of a for a real number a greater than 0 is defined as Let a be greater than 0 be a positive real number and n is an integer. Then n square root of a is equal to b if b to the power n is equal to a. In the language of exponents, we define n square root of a can be written as a raised to the power 1 by n. In particular, cube root of 2 can be written as 2 raised to the power 1 by 3. If cube root of 8 is equal to x, this can be written as x cube is equal to 8. Now let's take this example. Cube root of 8 is equal to 2. So this we can write it as 2 cube is equal to 8. Similarly, 4th root of 16 is equal to 2. So this can be written as 2 raised to the power 4, which is equal to 16. In general, if nth root of positive real number a is equal to b, this implies b power n is equal to a. We now have the following extended laws of exponents. Let a be greater than 0 be a real number and p and q be rational numbers. Then we have the following laws. Now consider the example. Here 3 are the two bases and exponents 1 by 3 and 2 by 3. Now let's simplify. We get 3. Based on these examples, you can generalize the first law. Consider the next example. 3 raised to the power 11 upon 3 divided by 3 raised to 2 upon 3. Using the second law of exponent, we express this as follows. On simplifying, we get 3 raised to the power 3. Thus, the second law is verified. Now verify the third law of exponent. Consider the next example. 3 raised to the power 4 by 2 the whole power 2 and 3 to the power 4. Can you see a relationship between the exponents of these two terms? Let's examine the first term. Applying the first law of exponents, we could express this term as follows. On simplifying the first term, we arrive at the fact that the two terms are equal. You can do this by another method. 3 raised to the power 4 by 2 the whole power 2 can also be written as 3 raised to the power 4 by 2 into 2. This can also be written as 3 raised to the power 4 into 2 by 2. After cancelling the 2's, we get 3 raised to the power 4. From this example, we can generalize the third law. Now come to the fourth identity. Consider the example. 5 raised to the power 3 is equal to 5 raised to the power 1 by 3 into 3. Cancel out these 3's, we get 5. Based on this example, you can generalize the fourth law. Summary. Let's summarize the topic. Numbers that can be written in the form of p by q, where p and q are integers and q not equal to 0 are called rational numbers. The collection of rational numbers is denoted by q. For example, 2 by 5, 99 by 4, minus 214 by 35, etc. Numbers which cannot be expressed in the form of p by q, where p and q are integers and q not equal to 0. The collection of irrational numbers is denoted by s. For example, root 2, root 3, root 5, etc. The collection of all rational numbers and irrational numbers together is the set of real numbers. It is denoted by capital R. A real number is either a rational number or an irrational number. The decimal expansion of a rational number is either terminating or non-terminating recurring. In a division, if remainder becomes 0 after a certain stage, then the decimal expansion is terminating. If the remainder never becomes 0 but repeats after a certain stage, then the decimal expansion is non-terminating recurring. A rational number can be expressed as its decimal expansion. The decimal expansion of a rational number is either terminating or non-terminating recurring. The decimal expansion of an irrational number is non-terminating non-recurring. every real number can be represented on a number line uniquely. Also, every point on the number line represents one and only one real number. The process of visualization of representing a decimal expansion on the number line is known as the process of successive magnification. If R is a rational number and S is an irrational number, then sum and difference of them are irrational numbers and product and division of them are irrational numbers. R not equal to 0. The following identities hold if A and B are positive real number. To rationalize the denominator of 1 by square root of A plus B, we multiply this by square root of A minus B by square root of A minus B, where A and B are integers. Let A be greater than 0, be a real number, and P and Q be rational numbers. Then we have